that looks good. Okay.
Sorry about that.
That's fine, totally fine. So now we will have our second speaker, Stephan from the Texas A&M University. I believe he just joined this fall as an assistant professor. And today he will be talking about on the solution of PDEs in the space of neural net functions. So the screen is yours, Stephan.
Thank you so much. So I'm very glad to be here. I'm very sad, obviously, to not be in person with you, but it's such a pleasure to be here at this workshop. And so I'm going to talk about something which is technically simple, but I think which has interesting philosophical potential. So the kind of starting point for our considerations with Weinan E was that there are many methods where you can solve low-dimensional partial differential equations, but in high-dimensional PDEs, things become difficult because of the recursive dimensionality. And there are certain applications where we really want to solve high-dimensional PDEs. So since neural networks have been so successful at beating the curse of dimensionality in other fields, there was a lot of interest in seeing whether they could do that for partial differential equations as well. And I think starting in about 2017, there was a series of works that initiated that. And indeed, in certain applications, it can be proved that the solution of a PDE can be approximated by neural networks without the curse of dimensionality if the data of the PDE can be approximated without the curse of dimensionality. So if there is a diffusion equation, we need something on the diffusion equation, diffusion coefficients to approximate them. But if the data is nice, the solution is nice. And I think Lucas Gonan, I saw in the audience, would probably be able to say a lot more about that, or Arnulf Jensen. But we then were curious about whether we could extend this, in a sense, to a more classical setting of partial differential equations where we use functional analysis tools. So the motivation of that is that if it's generally possible to show that the solution can be approximated without the curse of dimensionality, but due to the techniques, we've got very little control on the size of the coefficients of a neural network. And obviously, if we've got huge coefficients and there are some miraculous, tricky cancellations, then it is very hard to glean those from a finite amount of data. So the larger the coefficients are on average, the rougher the function profile can be, the harder it becomes to learn what the function should be. So we were interested in function spaces which are more adapted to neural networks specifically than just any neural network with any size of coefficients, and not just controlling the number of coefficients. So classical numerical analysis would proceed in a series of steps. We prove the regularity of solutions. Then we approximate, then we've got an approximation theoretic part, which is just approximating elements in a function space. And then we design a numerical method that brings those together. And today I'm basically going to focus on the regularity of solutions, but in function spaces which are more designed to deal with neural networks. So the probably classically most studied case is that of shallow neural networks because it is most approachable, at least initially, and the hope is that it will guide the development also in the theory of deeper neural networks. So a function is called a Barron function due to Andrew Barron. If there exists a probability distribution such that f can be written as the expectation of a times activation function applied to an affine function of the input x. So in a finite neural network, we would have this affine function here, apply the activation function coordinate-wise, and then have another linear function outside. In the case of infinitely wide networks, instead of having a sum, we take an expectation. This could also be an integral. The math does not change, but having it be an expectation makes some arguments a bit more natural. And this would correspond, if you want to, just write a 1 over m in front of the definition of a neural network, and you'll be fine. And here to introduce a norm, we need something like moment bounds. These moment bounds also guarantee that the integral on the left-hand side converges. So one of the nice things is that if there exists a probability distribution and we've got a Barron function, then here the function can be approximated by a finite neural network. So there could be a 1 over m here that would maybe make it a bit more intuitive. With rate 1 over square root m, and here we've got the Barron norm, it's homogeneous, and we've got the second moments of the data distribution. So with m neurons, we can approximate any such function up to accuracy 1 over square root m, which is wild in high dimension. None of this depends on the dimension at all. And indeed, Barron space is so large that no linear method could evade the curse of dimensionality here. So whatever linear ansatz space you choose, you will have something that where the approximation quality scales like m to the 1 over d roughly, where m is the dimension of the space. So this is a reasonably large function space, which has good approximation properties, and that's why we like to study it. Now, the other reason is that if we've got a set of n data points, then with high probability, the average of a function over those n data points is pretty close to the integral over the distribution with respect to which these data points were drawn. And that's uniformly over the entire unit ball in Barron space. So if we normally, if we were to minimize, to try and optimize a function so that it fits certain criteria on these finite data points, then this finite collection of data points would not really tell us anything anymore about the average integral. But because Barron space is reasonably restrictive still, even if there is a correlation between the data points and the parameter where you're evaluating, the Monte Carlo integral will still be useful. And that is incredibly important in machine learning, where everything that we do is an approximation over finite data. So these, I think, are the underlying reasons why Barron spaces are so popular as a starting point. And on the other hand, we can understand a few things analytically about Barron functions. I'm just going to point out 2 of them. So we are starting from a structure theorem. If we've got a Barron function, then we can decompose it as a sum of Barron functions, where the first one is C1, and then the others are C1 except at the origin, and they depend on some orthogonal projection, some affine map. So basically what we've got is something that is a function which is C1 except along some lower dimensional subspaces. And that is a fairly strong restriction on the singular set of a function. And there are 2 immediate corollaries, namely if we've got a diffeomorphism which preserves Barron space, so a change of variables in Rd, which preserves Barron space, then the change of variables is necessarily affine. And the product of 2 Barron functions is not generally a Barron function. So I'm thinking about ReLU when I'm saying this. And you can, if you multiply 2 ReLUs at an angle, then the singular set will have a corner somewhere. So this this gives us a bit of insight, I think, into the function spaces that we're dealing with. And then we were curious about regularity theory in them. And I think it's easy to see that, well, if we can't change our variables and if we can't multiply functions, then a direct imitation of Schauder theory is going to be very hard. And that is indeed the case. So we started looking at things a bit more elementary and tried to imitate basically what Evans chapter 2 does. And this is an important remark, but the product of two bounded Barron functions is a composition of two Barron functions. So there may be some hope if we allow deeper networks. But in certain simple cases, Barron spaces are perfectly well. So first off, a negative example, if we just try to solve the Poisson equation, then the solution is generally not in Barron space. And the reason is that if we've got ReLU as the activation, and we've got a right-hand side that is just ReLU applied to one coordinate, then the solution is equal to sigma of x1 to the 3 divided by 6 plus some harmonic function. And if this harmonic function were to grow slower than 1 over x to the 3, then it would be a harmonic polynomial of degree less or equal to 3. And so if u grows like x to the 3 in some direction, so u grows like x to the 3 in some direction or faster, but Barron functions are Lipschitz, so this is not a Barron function. On the other hand, if you were to change the activation function on the right-hand side, probably more could be said. In the case of the screen Poisson equation, though, where we exert some pressure downwards, then we can prove that if the right-hand side is a Barron function, then we do get a Barron function again with slightly different results depending on whether our activation function is bounded or ReLU. And the proof is just a direct computation we convolve with a 3D Green's function. And essentially, if we can do it in 3D, then we can do it in any higher dimension, because all we need, the right-hand side is a superposition of functions which only depend on one variable. So using the superposition with functions that depend on 3 variables and then averaging over our space or choice of a 3-dimensional space, we get the correct function in any dimension. Similar things can be done for the heat equation. So here we've got an initial condition that depends on the, that is a Barron function. And we just write down the heat kernel, exchange the order of integration, we get an expectation outside, and we use this average integral and a change of variables. And then we see that this is indeed of the same form, where the expectation now is given with respect to a smoothed out measure. But this is a Barron function in x and square root t due to the parabolic scaling with a certain bound on the Barron norm. And it's a Barron function in x only for fixed time t, where the Barron norm can grow because there's a square root t here that gets absorbed into the bias. This could probably be avoided a little bit if you modify your Barron norm and what exactly you measure. But only the second estimate really carries over to the inhomogeneous heat equation because there's parabolic scaling. And so if we had a right-hand side, then we would get basically a superposition of functions which are Barron in square root t minus t1, square root t minus t2, square root t minus t3, and so on. And so we don't get anything that is barren in time necessarily. This can be extended a little bit to a nonlinear setting. So if we look at viscous Hamilton-Jacobi equations, then this is a nonlinear PDE, which can be related to a linear PDE by saying we solve the heat equation with a modified initial condition, and then we take the logarithm to reduce it back to something that is related to the original PDE. And the theorem is that these two are related. So if we are on a bounded interval, we can represent the exponential function and the logarithm function as Barron functions. This is just inserting the one-dimensional the definitions into one dimension and doing the calculation, and using that Rayleigh is a fundamental solution for the one-dimensional Laplace equation. So we can represent this exponential function here. So we can represent x of u naught as the composition of two Barron functions. Then we solve the heat equation, and we know that this is a Barron function in square root t and x. And here, then we can take the logarithm, and that gives us a Barron function again. So if we we know that if we've got two or multiple two-layer neural networks, then the composition is a three-layer network, because here all we need to do is to combine the two linear maps that are at the input and output layers of the two neural networks into a single linear map or a fine map. And the conditions on what it means to be Barron translate into a condition on the size of the coefficients of this matrix in the middle. And so similarly, we can do the same thing for an infinitely wide neural network. And instead of getting a three-layer neural network, we get a composition of Barron functions, which is, for example, in a function space for three-layer neural network. And we get a norm estimate, which is nonlinear, and it depends massively on the oscillation of the function u naught. So shifting it up or down doesn't really make a difference for us, but the difference between the supremum and the infimum enters exponentially. Thus, in the case where we've got a nonlinear PDE, I think the takeaway is that we still can occasionally guarantee that the solution can be represented by a neural network, but we will generally need deeper neural networks, and the bounds may depend on the also on the L infinity norm of the initial condition, not just the Barron norm. So all of this, all of what I've said so far has been, well, we take a Green's function and we take and we do the explicit calculation, and things work out because we've got this kind of translation invariance in the differential operator. If we introduce boundary conditions, all of this breaks because there's no translation invariance anymore, and things become more complicated. I'm going to actually, well, I can sketch it briefly, but if we solve if we look for a harmonic map and the boundary values are in Barron space, then it feels like a very weak requirement to say that the solution would be in Barron space, because we're not even asking for differentiability. And harmonic functions are extremely smooth. Nevertheless, it's not true, as you can see by the structure theorem, because the equator where Rayleigh has its breaking point is part of the set where u is not differentiable, but the central plane is not, because harmonic functions are smooth inside the unit ball. and then this is incompatible with the structure theorem for Barron functions. So if D is greater than 2, then U is not a Barron function. We've since found an easier argument, namely we just look at the half space, then we solve the Poisson equation, we look for a harmonic function with Rayleigh boundary values again. And for this, we can write down an explicit formula plus some harmonic function. But especially if we look at one point, this harmonic function won't matter that much because it's a harmonic function with 0 boundary values. It's going to be smooth. This guy, however, we've got a y times log y close to the origin when x is equal to 0. And that is not a Lipschitz function. So it cannot be a Barron function or a composition of Barron functions or in anything associated to neural networks. So you cannot be represented by a neural network of any depth. So having non-homogeneous boundary conditions really messes with things. So as a summary, for translation invariant linear PDEs, we can often show that solutions lie in Barron space just by using the Green's function. But boundary conditions really break translation invariance. And even for harmonic functions, if the boundary values are given by a neural network, then the solution may well not be. But if we relax what we are trying to do, so we were looking at non-homogeneous Dirichlet boundary data, and that turns out to be difficult. But in a slightly different setting, Jianfeng Liu and Yulong Liu obtained positive results for elliptic equations with homogeneous Neumann boundary condition and in a slightly different kind of Barron space. So there is hope, even without going to deeper neural networks, but we need to be very mindful of what we want to do. And nonlinear PDEs may require deeper networks, so something like compositions of Barron functions. This is where our initial thoughts about irregularity theory in spaces of neural networks have gone. And I think it's a promising direction. It's also a promising direction in the sense that this may actually give us some insight into why deeper neural networks are sometimes as crucial as they are compared to shallow neural networks, possibly beyond the scope of solving partial differential equations. And with that, I'd like to thank you for your attention and thank you for the invitation.
Great, thank you, Stephan, for giving this insightful talk. I saw already a question from the audience. Yuri, would you like to unmute yourself and ask question out loud? Is the question asked by the audience in the room? I feel the Zoom. Yeah, okay, it's unmuted now.
Hello, can you hear me?
Yes, I can hear you.
Oh, great. Now you can. Great talk, thank you very much. I was just wondering, it seems that most of your proofs are along the lines, let's find an analytic solution of some problem and show that it is a Barron function or something similar. Are there any other ideas or any other methods that you think could be useful to prove such results?
It depends a little bit on what you're looking. I think not at the stage that we are at right now, mostly because so my background is in elliptic PDEs, and I grew up with Schauder theory. So basically what you do is you have a very good understanding of a problem, say constant coefficients, whole space, everything's like the data are compactly supported, and then you prove something. And it turns, and then you change, you take freeze your coefficients, you change variables, you work with the boundary case, etc. And then you piece everything together with a partition of unity. And so what we found was that changing variables doesn't preserve Barron space, and taking products doesn't preserve Barron space, and even coming up with a partition of unity, you need deeper neural networks. So I think at the moment, once we've got regularity in some space of neural networks, we can say, okay, and now we go deeper, we take compositions of these neural networks, and then we can piece everything together, and it's nice. But the problem, I think, is the first step, where we don't actually have a good regularity theory, especially the fact that for harmonic functions with neural network boundary data, we don't get neural network representations, feels like it's a major obstacle. So I feel like it would be nice to get something better, possibly for deep networks, but we don't even understand the basic case. And that is still where, even in the classical theory, you look at representation formulas and obtain your estimates. So I think there is a lot of work to be done, and I don't think we're quite at the stage yet where we can really use more abstract tools. But I might be wrong, and things evolve very, very quickly in this area.
Yeah, well, thank you very much. That makes sense.
I saw another question from the online audience from Frederick Weber. Would you like to ask a question by yourself, or I can read it aloud?
Can you hear me?
Yes.
I was just wondering for whether there exist any such regularity results when your initial condition is again a Barron function for a fractional heat equation on the full space, because you have this mainly relates to slide 7, like in the heat equation case, you have similar representation formulas, of course, also for the fractional heat equation case. Yes. And maybe something, is there something known over there? Although you, of course, have not these specific representations like in the Euclidean heat case.
So I thought about this for a while. And in the case of Laplace to the 1/2, you actually do have an explicit formula. And I think you could do very similar things. And in the case Laplace equals to 1/2, you would even get rid of this pesky parabolic scaling, because space and time suddenly scale the same way. And you could hope to prove nicer results. The issue I see is purely technical with ReLU, because ReLU grows linearly, and that is the borderline case where the heat kernel of order 1/2 stops to be integrable. And so if you change your activation function to something that avoids that, I don't see any super technical difficulties to go through, but I'm also not aware that anybody has ever done it. If you have the fractional order bigger than 1/2, you could probably even do it for ReLU.
Okay, thank you. That makes sense.
Another question from the audience? I have one more question from Stephan. So have you tried to look for solutions in other spaces, like the flow-induced function space, which corresponds to the residual neural network, the limit of the residual neural network? Mm-hmm.
So I think I've thought about the residual function, the residual networks at some point. The issue with the flow-induced function space is that it's not a linear space. The reason being that essentially you're solving an ODE, and the right-hand side is given by Barron functions. So in a sense, the residual blocks are infinitely wide, but the space that you keep, the space where the ODE evolves, is finite. And so that gives you something where at least we have not proved yet that it is a linear space. And so a lot of these tools, we take a superposition of functions, just don't work anymore. On the other hand, if you wanted to solve something like a transport equation, where you mostly solve how particles evolve, and then apply a single function to it, I think that is something that the flow-induced function space would be great at. So I believe it depends on the nature of the PDE that you're solving. And for equations with a diffusion contribution, I imagine you can prove things, but you will have to make your ResNet very wide, and that is a little bit against the spirit of using resonance.
Yes, that's correct. Yeah. Yeah. Thank you. Thanks. Other questions? Okay, great. So this brings an end to the first session in the afternoon. I believe we will have about 20 to 30 minutes for the break, and then the next talk will resume at 4 p.m. Okay, thank you.
Thank you.
Mm-hmm.